All right, so welcome everyone to this ECP tutorial about auto-tuning ECP applications with this GPTune package, which is the product developed in the XSDK effort through ECP. We have a big team. So the current active members are myself, Yang Liu, and Yang Hun Chou. We are the main speakers today. And then there's Henry Law and Sherry Lee and James Demo. So the plan of today is we're going to split this tutorial into mainly three parts. And each part comes with the first presentation, follows by a hands-on. Then we have a 10 minutes break in between. So the first part would be mainly an introduction to ECP application and their auto-tuning, some basics of Gaussian process, and the basic usage of GPTune. Then the second part will be advanced algorithms in GPTune, which is actually the main feature that we want to advertise. You'll get a chance to try each of these features with the accompanying tutorial examples. Then the third part would be about historical database and crowd tuning, which is in essence some sort of a shared database that you can upload and save the data onto the cloud and maybe use that to say for checkpoint purpose, for transfer learning purpose, etc. So we will also get a chance to learn that. So then the last 30 minutes we'll just wrap up, maybe with some Q&A and some survey. So we'll be able to send the survey later. Okay, so first let's get some introduction of the auto-tuning of ECP applications. So what is auto-tuning? So let's say we're given a target problem and a parameterized code to simulate or compute it. So suppose we have some sort of parameter configurations that consume or accuracy you achieve, etc. And as you know, many ECP applications are very expensive, so it requires lots of compute nodes for a long time, even for a single run. So the goal is to make best use of the limited budget or limited number of samples to get the best best performing tuning parameters. So this is a simple example with the QR routine in Scalapack. This figure shows a 5x5 sparse matrix, a dense matrix distributed with a 2x2 process grid. And here we're using this row-wise blocking parameter and column blocking parameter, both to be 2. So the essential block, tile of the computation is 2x2. So let's see. We're given a fixed number of compute nodes, and let's say we just take a matrix of size m by n, and we can use this m n pair as the task to define a task. So suppose we want to consider these three parameters. There's row-wise and column-wise blocking parameter, and the row dimension of the process grid. And remember this: the total number of MPS are now fixed. So this is actually exhaustive search, semi-exhaustive search of the performance. So we're trying to tune the factor, the QR factor is in time. And this is the row-wise blocking parameter, column-wise blocking parameter, and then each layer of these things shows a specific configuration of process grid. So you can see this is a simple way of to visualize the object function of interest. You can see the variations can be very large. You can be factor 5 difference comparing the slowest and fast time, and if you look at the optimal parameter configuration, by conventional wisdom, we know that for the QR, distributed QR, the process grid usually want that to be as square as possible. And for the block size, it's usually also by default as square as possible is the best performance. But this is the optimal performance that we've seen after the exhaustive search. And so this is the 2000 by 2000 matrix, 10K by 10K matrix. But you can see neither of the blocking parameter or the process grid are as square as possible. So that means conventional wisdom is good, but in real time, in reality, many times we will need to use this this auto-tuning thing. So this is some characteristic of the object function of interest. So first, since it's a runtime or some statistics from running a real code, we don't have the like analytical form of the object function. Also meaning we don't have the gradient information, and the function evaluation can be very expensive, and it's non-convex and can have complicated form of constraints. And also the tuning parameter space can be consisting of real valued parameters, integer valued, or categorical ones. So this very complicated tuning task. And the one that GPTune relies on most is the well-known Bayesian optimization framework. So it's a model-based black box optimization framework. Here I'm going to briefly show some basics of Bayesian optimization. Suppose we have this object function y of tx. So here t can define a task, and x is the tuning parameter. So both of them can be multidimensional. So we're interested in the minimum of y. We're interested in finding the x that gives the minimum of y. So the way the Bayesian optimization works is we first assume that this y, this object function y, has follows some prior distribution. Normally, it's a zero mean the Gaussian process, and then we generate, say, n0 of the samples, pairs of of xy pairs, and then basically the Bayes theorem, we can actually refine this prior distribution into a posterior distribution, which is essentially the product of the likelihood times the prior probability. And in fact, we can assume this y follows some model f that is characterized by some hyperparameters. Then by maximize the likelihood of given these known samples, we can optimize the hyperparameters of the model f. Then after the model is built, we use the model to predict what is the next sample point. And for example, this xn plus 1, then we call the true object function to get yn plus 1. And then we go back, then we'll have one more pair of sample, and then we'll go back to this modeling, refine the model, then go to the search again, etc. Until we think somehow the function minimum has to be found, or the desired number of the function evaluation has been reached. So for the modeling, we realize several tasks. We'll briefly go through them. And for the search, it's actually based on the model. We can define this well-known acquisition function, and for example, the expected improvement that can be used to guide the search. Let's, for example, take a look at the modeling in more details. So suppose we assume this y of x follows a Gaussian process of fx, whose mean is mu of x and whose covariance is k of x prime. Again, here we'll assume this mu of x is I'm sorry. So has a zero mean as a prior distribution. So usually we can take different form, assume different form of the kernel, covariance kernel. Here it's a simple example of the Gaussian kernel, which is characterized by the length scale of each dimension d of the parameter space and this variance sigma square. Of course, GPTune can support many other different kernels if you wish. So this hyperparameters Li and the sigma square can be optimized by maximizing the log likelihood of this kernel. This model F given a set of observations. So once this model is built, then suppose we already also have this X and Y observations. Then we can, for any given unseen new point X star, we can use this posterior distribution to predict the mean at that X star and the variance at that X star. And based on this mean and variance, we can define this acquisition function. For example, this expected improvement. You can say it's based on the mu star and sigma star. And we can use some sort of a search algorithm, for example, genetic algorithm or LBFGS, to find the xi star that maximizes the acquisition function. And that's our next promising point that we want to call the true expansive evaluation. This is a simple illustration. So suppose we start with 5 initial samples in red. And the blue is the true object function with some variance, some noise, small noise. And the black is the mean predicted by the model. And the shaded area is the variance predicted by the model. Then we know that at these red dots, there's 0 variance. And the further away from this red dot, the variance is larger. And if you look at suppose this model is built here, and now you look at the acquisition function based on the model, that basically shows that this point has the maximum acquisition function value and suggests this is the one you should sample next. So, okay, so we now add this point, which is this red dot, into the observation, and we can update this model. Now the acquisition function looks like this. And now the maximum point is here. Then you add I think this point, and you keep updating until in the end the predicted model fits well with the true object function. And one of the main workforce in GPTune or the feature of GPTune is we not only consider single task tuning, but also this so-called multi-task tuning. Meaning we can have a set of correlated tasks. If you think of this QR example, the optimal parameters that for a given pair of m and n may also be the optimal parameters or near optimal parameters for another pair of m and n. So if you can build some sort of joint probability distribution among these different multiple tasks, then you can better use the limited budgets to build a better models and find a better optimal. The way it works is based on this so-called localized coregionalization model, or LCM. It's essentially, let's say, assume that we have a delta number of tasks yi of x, and each of them follows a GP, the fi of x. The LCM assumes that each of the fix is essentially a linear combination of q independent Gaussian process uq. So each of the uq is characterized by its own covariance kernel with its own hyperparameters. So this liq sigma q square and this linear combination coefficients are the three types of hyperparameters that we're going to optimize in the modeling phase. Then essentially we have a larger compared to single task tuning, single task modeling. Here we have this joint kernel, so that the correlation matrix K essentially is much larger. By default, it's a size that of number of tasks delta times the number of sample per task, but we don't have to limit ourselves to the fact that each task had to have the same number of samples. But essentially, this is how it looks like. This is a simple example of multitask tuning. Suppose we have these 3 tasks. So this is 1, 2, and 0 actually realization of different tasks from the T. And you can say if you model each of them individually, so the blue is the true object function. So we have some noise, so it's very noisy. Then the model, the mean is very, very bad, and the covariance is also the gray shaded area is also like a not very good catch of the true function for the 3 tasks. But if we have the same number of samples, but using the LCM model, then you can see it will actually much better capture the true shape of the functions. So that's the main workforce of the GPTune software. Here's a real example of scalable QR. So here we use 64 Cori Hashwell nodes, and I think we pick 10 metrics of different sizes, and we're tuning again the row-wise blocking parameter, column-wise blocking parameter, and the row-wise shape of the process grid. And this shows the ratio of the best runtime of GPTune versus 2 other tuners. Essentially, the higher than 1 means GPTune is better. So you can see 7 out of the 10 tasks GPTune is better, and 8 of the 10 tasks GPTune is better compared to the 2 other tuners. So here only show the multitask learning by every iteration we increase the sample size for each task. But of course, this LCM model can also be used in the transfer learning context, meaning you only focus on one particular task using existing data for other tasks. So see the part 3 for more details. So a few words about the GPTune software. So the majority of the software is written in Python, and it comes with a rich of different example bash script, and it also has a small C kernel for the core computation. It's part of the XDK. It's in the E4S release and also in the spec developer branch for sure. So in terms of user input, these are the mandatory ones. So essentially, you need to define input space for the application. Tuning parameter space can be categorical, integer, or real valued for each of them. And then the object function in secured example is the runtime. And you need to write by default, you need to write a Python, small Python code that launch the application, right? The Python launch the HPC code. And optionally, you can also define, say, some sort of constants in the tuning, all different type of constraints with, in the form of strings. And you can define, a coarse or analytical performance model, and you can choose, different algorithms, etc. So let's see how much time I have used. So, so the GPTune software relies on this so-called Autotune common interface, and with that we can actually write a small wrapper that links this GPTune to different other tuners. In fact, we can call the GPTune tuner or some variant, for example, the multi-fidelity one called GPTune band, or the non-smooth one called CGP or cluster GP. Those 3 are written inside GPTune. We can also call 2 external ones, for example, the autotuner and hyperbandster. You can say it's a single liner, then you get the results of a different tuner, as long as we follow the same autotune interface, meaning we define the same input parameter space, tuning parameter space, output space, objectives, constraints, etc., with the same interface. So I think we are approaching the first part of hands-on. So if you first, so there's the preparation of the hands-on I mentioned in the very beginning. So I suggest you to get this to work. And then let's say we have all the way to say 310 to work on the part one hands-on. So let me briefly walk through the part one hands-on. So what it does is once you have the Docker or have the Oasis account available, you kind of pull the pre-built GPTune Docker image, set up the runtime variables due to your machine, and run a simple demo example. And also there's a spec version, the installation and testing version that you can try as well. Let's see. So yeah, you can follow these instructions. So let me just show them in real time. So this is my machine. So I just do Docker run, then the image name. Here I'm in the Docker. Then so you can say under the examples folder, there's many examples you can try. But for this part one, we're going to focus on the simple GPTune demo. In fact, under this folder, there's also a few scripts, but let me show how this works. All right. So first you need go to the root directory of GPTune. Then there is a run_env.sh, which will set the runtime variables based on your machine. So for this tutorial, we're going to use the Docker, so we don't want to mess up with the different namings of your machines. So we'll just assume that the machine is some sort of with this kind of characteristics. And make sure you set the number of CPU cores of your machine correctly here. So you can, it's all listed in the hands-on. You should follow that. So for example, in this machine I have 4 cores. So once I change that, then I go to this example folder. Then there is a run_examples.sh, basically in each of the example folder. And for example, this is the simple synthetic function. And here we will use that function to illustrate a few features of GPTune. For this part one, we'll just do a basic functionality test. So here, there are some command line options. For example, the number of tasks you want randomly generated, and the number of samples per task. So let's see. Let's give it 1 task and 50 examples. Let's just run that. So you can see there are half of the samples are generated as the initial samples by random. Then you will run 25 iterations, and each of them generate 1 new sample. So in total you'll get 50 in total. And then in the end, this will show all the samples you tried. For example, this is the first task. Since we only specify 1 task, this is the task. This is a task parameter. This all the tuning parameters you tried. It's a 1-dimensional problem. There are 50 of them. It's also a single object tuning, so there's 50 function values. And then in the end, it shows what's the best function value and what's the best performance tuning parameter. And this is the 19th sample out of the 50. Also, you can look at this thing, which is essentially statistics of different stages of the tuner. For example, this takes about 17 seconds. That's the time spent in function evaluation. This is a simple synthetic function, but for most of the ECP applications, you will see the main cost of the tuning is this part, the function evaluation. This initial sample time, search time, model time, and etc. The things you can play with a little bit. Another thing I want to mention is here you can choose different tuners. Right? This is the GPTune tuner, but you can say choose, for example, OpenTuner. OpenTuner. Here we go. So then you can also try to compare, the specs value across different tuners. So aside from that, we also have a spec version of the GPTune installed in the Docker. So I assume you can already do something while I'm typing, so that we can kind of at the same page. So you can simply do spec install GPTune with some specifiers. Okay. So the dependencies of GPTune has been installed through spec. So here, it's pretty quick. So once that's installed, let's do spec load GPTune. It will essentially load some of the invariant variables. Then spec test GPTune. Test run. Sorry, spec test run GPTune. This will run a few predefined smoke tests in GPTune, including the synthetic function, QR factorization, probably also the superior example. So this will take a while, maybe 5 minutes. So I'm going to kill it, but you will be able to finish it, I think, in the first part with the tutorial. All right. Yeah. So if you have a question with the hands on, let me or Yang Hui or Sherry know. And yeah, we'll have about 7 minutes left.
So Yang, there was a question about accessing the cluster. So you can check out the our chat logs there.
So let's see, which one?
So Amy Powell asked about accessing the cluster because it seems like the access was blocked or locked or for some reason. So
I mean, there's no space here, so just make sure you're using the correct username. So Amy, do you still have a problem?
I can try. I can try again. I may have been locked out, but let me try again.
Okay, so
I've added the name for the student 20. If that still doesn't work, then maybe we can assign another account.
True. I mean, I don't think all the people listed here are present, so maybe we can reassign Amy to someone else if this account has an issue. But Yang Hui, did you try this? Did this one work for you?
Yes.
Then I believe maybe you typed the username or password wrong.
So Yang, how did you do the assignment?
I just look at the names from the whole app.
I see. A lot of them they don't use. We can reuse.
Right.
So for example, I know a lot of them are not here.
Yes. Let's see.
So maybe we can reassign. Right now, Amy is which account is Amy? It's 20.
Yeah.
Okay. Can you try 4? I don't think Valerie will be using this. In the Google Doc, so Amy, can you try 4? It's a student 04.
Let me see. Okay. Oh, so I should use student04 as my username?
Yeah, and the log password is 0, starting with a 0 AC.
Okay,
blah, blah,
let me
blah.
try that. Okay, that worked. I'm on.
Very good. Okay.
Hooray.
Are there anyone who don't have who are not assigned to any account and you want to do a hands-on exercise? I think, Yang, we can also remove higher. So that opens up another one.
Yeah, for the part one, I would say like if you were able to run this run underscore example.sh under that example folder, then you should be all good to go. If you have extra time, you can try to play with different options. So Matt Barker, we're assigning to student 09. Sure. Yeah. Okay. So now it's we have a 10-minute break. So feel free to try it further. We'll resume the second part presentation in 10 minutes. All right. Okay. Let me type that.
Hey, it's Matt. Yeah, I guess I understand how to put in the username. What's the password?
It's the second column. Do you have access to this?
Oh, I see. Gotcha. Thank you.
Yeah. Let me try to sing this one. Yeah, if you are using this Oasis machine, then at this line, you need to set this core to be 26, so that you can see more performance in the later part of the tutorial. And I forgot to mention that after you run this simple example, you will see under the subfolder GPTune.db, there's a database in JSON format that essentially record every run of the sample. Maybe I can also show the how the Python driver works for that simple example. So for the part one, we're just looking at the simple Python driver. You can see that we're actually reading the command line options here. And this is fully user customizable. So if you have your own application, it's something you can write it by your own. Then we call this function to actually read the machine information from a meta file that was generated by this by setting up the runtime variable. It will generate a file. And so here we define the input space, which is this t, it's a real number in the range of 0 to 10. And then the parameter is x in the range of 0 to 1. Output space is just a single objective, unbounded. We have some constraints in the form of Python strings. Then we define the tuning problem, and we define the we tell GPTune number of nodes and cores, and we initialize the options. You can try to change these options, play with it a little bit. Then you can say based on the tuner you choose, you can do GPTune or OpenTuner. Or Hypermaster, or CTP, which we'll talk about in the next session, etc. So you can see their interfaces are pretty similar. It's just single line and set up the runtime environment with this run_env.sh. That by running that, this will be run after once you run this run example.sh, that will run this thing first, and it will generate a meta file here. Essentially defines the application name and then the machine information. So processor type. Again, this is Docker, so we don't want to mess up with this name. So we just say unknown. It's one node for coarse. Then there's some dependencies while we installed while the GPTune was installed, which are OpenMPI versions, scalable versions, GCC versions, etc. As you will see in the part 3, this will be used to share data with the core database. Let's also try to run this spec test. So Mike, are you using the Oasis account or your own machine? I think you're using the.
I'm on the Oasis account.
So once you're on the account, do SSH Saturn. No, it's in the. Follow this. So I think you are here.
I'm sorry. Yes, got it.
Yes. Then just do this Docker run it.
Thanks. Yeah, I missed that part. I missed that part.
And in the meantime, if you have any questions regarding the presentation, feel free to ask or send in the chat. Okay, so Kim has a few questions. Is it possible to have nonlinear constraints or constraints that relies on multiple variables? Yes, so the constraints in GPTune is specified by a form of strings. So if you have multiple variables or even some constants, there's a way in GPTune interface to define the constant name and values, and you can use all these names to write a string and used as a constraint. And is it possible to start with a user-defined prior distribution? That's a very good question. That's something we'll plan to add into GPTune real soon, but currently it's only like a zero-min prior distribution. Can we evaluate multiple expensive simulation concurrently using multiple MPI nodes and update the surrogate with multiple samples during one iteration? So first, yes, we can. There's two questions. The first question is, yes, we can we can run multiple samples at the same time. There's an option called sample parallelism or something like that, so that you can define the number of cores or nodes used per sample, and based on that, it will calculate how many instances it can launch based on the total number of cores available. However, it's useful if you do the initial samples, because you essentially launch those samples can launch something in parallel. But during the modeling and the iteration phase, by default, we only add one sample per iteration. So that means there you probably need to do one function evaluation at a time. We do have a like a beta version that can generate multiple samples per iteration. Then there you can also do parallel execution, but that's a better feature. Right. Okay, I think it's time to move to part 2. So after we introduced some basics of the auto-tuning and basics of the GPTune, now let's move on some of the main features of GPTune. And this part will have a 40 minutes presentation with 30 minutes hands-on. The presentation will focus on essentially all the features listed here, one by one. So we have a parallel framework that can do some acceleration of the tuner itself. And we support advanced multi-object tuning. We can import like analytical performance model into the tuning experiment. And then we can do multi-fidelity tuning. And finally, for functions that are non-smooth in nature, we can do this so-called clustered GP algorithms. And many of these tools, these algorithms actually can be combined into the basic feature of GPTune, which is multitask tuning. So by combining these different features, you will see very interesting, intriguing results. And in the hands-on, we'll have examples. We have the synthetic function as well, but we also have 2 or 3 real applications like a QR, sparse metric factorization in SuperLU and multi-grid using in Hyper. And we will use them to demonstrate each of these features. Okay. So first, let's talk about the parallel architecture of GPTune. Essentially, there's 3 modes of GPTune. And the default one is this so-called MPS spawning mode. This is the workflow of how it works. So essentially, we will need to do, say, MPI run -n1, then the driver script. Then the driver script will launch GPTune that will go through this loop, sample, model, and search, and go back to sample. In the sampling, we use the MPS spawn to, in essence, launch the HPC code. Presumably, the HPC code is also MPI based. And of course, you can do multiple HPC code samples in parallel, also with this spawning mechanism. And for the model phase, since the modeling is the most expensive part inside the tuner, which is suppose the coarse matrix is size n by n, that cost is n cube. So essentially, we can use the we can also use MP spawning to use multiple MPIs to accelerate the modeling phase. And in the search phase, if we have multiple tasks, then the search of each task is essentially independent. So there we can use the number of MPIs as number of tasks to also do some acceleration. And it does so this spawning mode actually again calls the application HPC code from inside Python. It supports these parallel phases, stages. However, it does require a slight code instrument of the application to hook up with this spawning APIs. We will show them real quick. I mean, we'll see them later. And then there's a lightweighted version of GPTune, which remove all the MPI dependencies. Most of the MPI dependencies. So that means we don't support any parallel execution of the modeling and the search phases, and we don't support MPS spawning. So many times you have to call the HPC through Python by, say calling a bash script, which will do MPI run instead of bash script of the application. We found that this kind of a approach typically has very large overhead on many DOE machines. So So we wouldn't suggest you're using this one for real application or real MPI-based applications. Then there's a third option called reverse communication interface, which is slightly different than these two. It also kind of removes the MPI dependency of GPTune, but it doesn't sacrifice the performance. I mean, it doesn't have much overhead per application launch. The way it works is instead of this tool, we have a Python driver. Here we have a bash driver. So the bash driver will keep querying GPTune for the next sample. And then you read the history database to identify which samples GPTune asks you to evaluate. Then in that bash script, you just do npm run srun js1 of the application with that particular configuration, get the result, update the historic database, then call GPTune again for the next samples. So for most of that, the presentation here will use this default mode, but we'll have examples in the hands-on to show this RCI. And in the slides, I also have one pseudocode to demonstrate this RCI. Okay, so the first feature is the parallel performance of the tuning. So again, here assume it's a spawning mode, the default mode. Again, consider this simple synthetic function, one-dimensional tuning parameter, a task parameter, and a one-dimensional tuning parameter. Those are real valued. It's the same example you see in the part one hands-on. Here are 4 realizations of the different task parameter t equal to 1, 2, 4, and 6. As t increases, you can see the function becomes much more wiggling and much harder to optimize. But here the point is to demonstrate the parallel performance. So we will generate 20 of those applications. We'll generate 20 of those applications, and each application will say start with 20 samples each, and go all the way to 320 samples per task. Here we're comparing the parallel performance of 1 MPI versus 32 MPI for the modeling phase in blue and the search phase in black. So you can see as the number of samples per task increases, we see much better parallel performance of the tuner. The second feature we want to so there's an example you can try. We'll show that. You can try. I will show that later. And the second feature I want to show is the advanced multi-object tuning feature. As you may be familiar with, in multi-object tuning, in many cases we generate a bunch of samples, and from that bunch of samples we kind of identify a so-called Pareto front, meaning on that front. There's no sample on that front that will dominate over any other in all objectives. For example, this is another synthetic function called OSI. It's two objective tuning. So we have objective Y1, objective Y2. The black is the true Pareto front that we generated by initial doing a random sampling of essentially exhaustive search. After exhaustive search, we get this true objective, this Pareto front. So any point on this front does not dominate over the others in both objectives. And then we have different ways of specify the tuning problems. And for example, suppose we have Y1 and Y2 or more than 2 objectives. For each of them, there are 3 different ways to specify them. First is we don't have any constraint for the range of the objective. For example, it's -infinity to +infinity, and we're going to optimize that object function. That's the default way. Or you can have a constraint optimized variable. What I mean is here we have a range. For example, it's -infinity to 10. So every sample above 10 is not considered as a valid sample. And again, we're going to optimize this object as well. The third one is we have the constraint non-optimized variable or object output. So it still has a range, And here, what you care is you don't want to optimize this thing anymore. So as long as this objective is within this range, then you are okay. Then here we say optimize equal to false. So there's 3 different ways of specifying an output objective. And here, the default one is the red one. So and we compare the 3 with a same number of samples. So the red one, so it can be far off from the true Pareto front, and many samples, and it tends to not sample this region. So suppose you're interested in all the y1 values that is below minus 150, then this is not a good result. But if you can consider this green one, then it generates more towards this this range, which is constrained optimization on y1 and unconstrained on y2. Or you can do unconstrained on y2, but only specify a range for y1 without any optimization. That will generate this blue one. So you can say the behaviors of the 3 differs a lot. So that really depends on your need. So here it's a real example of tuning the factorization and the factor memory of the sparse matrix solver super LU disk. So here we use the matrix name to define a task. We predetermine the number of nodes and the coarse. And here are 4 tuning parameters of categorical and integer values. So again, we can consider 2 object tuning: the time and the memory. So if we consider a single task, this is one matrix, and this black dots lies on the Pareto front, and this blue one is the default parameter. You can see it's way from the optimal, as we have already been seeing in the QR example. As I said, all these features, most of the features can be combined with multitask feature. So here is a multitask, multi-fidelity example. Here we have 8 tasks, 8 matrices. So we want to do a 2 object tuning on all 8 tasks all at once. So the dashed ones, so each color is 1 matrix. The dashed ones is a single task tuning, and the solid ones are the multitask tuning. You can see for many of the matrices, the solid ones give you a slightly better performance. This is the pseudocode for the spawning mode, the default mode. This is what I mean by code instrument. So this is your application. This is your code. And suppose you have a main entrance. So the few liners you need to add is this MPI com get parent. Then you do whatever you do before. After you finish, you get the result. You communicate the result back to the communicator using the communicator you created. Then you disconnect. So this is on the application code part. Then in the main Python driver part, this is how you define the object function, taking the dictionary as the input. And then you can say it's setting environmental variables, command line options, etc. Here. But this is how you launch the application. It's based on this spawning. So this is the spawning API from the MPI4Py. This is your application name. And this reduce and disconnect actually match with this reduce and disconnect. So these few liners are very important in the spawning mode. And this is the rest part of the main driver, the main Python driver. You define the constraints. Again, you can define the constraint either as a string or as a function, as I should correct that. So the input of the constraints can be anything you defined as the input and the tuning parameter space or constants you define. It can be, so you can it can be any form, either linear or nonlinear. So it's essentially you take an input and return a true and a false. So that's how it's specified. So I can skip the rest. So essentially this, okay, so the input space again is a matrix name. The tuning parameter space is all these 4. So there's 1 categorical, 3 integers. And we're considering both the time and memory. And here is specifying two matrices, so the two task, two objective tuning, and they return the results. As I mentioned earlier, if you don't want to bother with the code instrument, then there's another option called this RCI, or reverse communication interface. So here the main driver is the bash driver. So this is how it looks like. You specify two objectives, time and memory, and this is the database that will be generated, or that will be used to communicate with GPTune. Then you have this main loop that each of the loop you will essentially query GPTune. Right? This is the driver, the main Python driver. You query the driver, and then you query the data. So the driver will update the database file. Then you query the database for the entries that require to be evaluated. You get the tuning and the input parameters from that entry, set up environment variables, then just call srun of the application. As what you normally do in a bash script, so there's no code instrument needed. Then to get the result, this particular example we show you can get the result from the run log. Right? This run log, get the run log, get this time and factor, time and memory, and read this thing back to the database file, and then call the Python driver again for the next sample, and etc. Until this while loop says, okay, GPTune is satisfied with all the samples. You don't need any more samples. So these are basically the main two modes, right? The MPS money mode and the RCI mode. Then the next feature is sometimes you can have a like analytical formula for that application. A simple example is you can have this. So the application operating function is y of t of x, but you can have a coarse model called y tilde of t of x. So it's a linear combination of three things. For the QR, it's this simple linear combination. So it's the number of flops and the number of communication message, number of communication volumes. Those can be computed, calculated through the size of matrix, total number of MPS, then the process grid shape, and the blocking parameters, etc. Then this combination coefficients, you can update them through, say, a simple linear regression, etc. So if you have this kind of model, then what GPTune can do is it can build this model into the tuning parameter space. So the tuning parameter space, suppose it's d-dimensional, now it's becoming a d+1 dimensional. And with this enrichment, sometimes you can get much better performance. We'll see that here. So as I mentioned, the performance model can also, the coarse model can also have its own hyperparameters. For example, these linear coefficients are the hyperparameter of this simple model. Then this is the MPS bounding based workflow. So the way to use the performance model is every time you generate new samples, we will use the new sample to update the model the analytical model's hyperparameters, then build it into the tuning parameter space and do the real model, and etc. So this figure shows that if you have a 5-task tuning example, and suppose you can afford 10 samples per application, or 20 or 40, and this is comparing the optimal found by GPTune with and without this analytical performance model. So above 1 means the analytical performance model helps. So you can see, because the model is really coarse, and you can see when the number of samples is small, it does give you a boost in terms of performance. But when the number of samples is large enough, then the coarse performance may not help you anymore. That's kind of expected. The way it works, the pseudocode is also very simple. Again, there's the example in the hands-on. So you define the model like this, exactly what I showed in the previous slide. And this is the update phase where you use the existing samples to update the coefficients, for example, with linear regression. And these coefficients are defined as constants into GPTune. Let's see how I'm doing. So it's how how long do I still have? Before the hands on? I think maybe 20, okay, maybe 20 minutes or 15 minutes. So the next feature is we can also do this multi-fidelity tune. The variant we developed through inside GPTune package is called GPTune band. The way it, I mean, the basically motivation is in many ECP applications, you actually, instead of the true objective function, which is very expensive, you can generate, a cheaper variant of the objective function, which is much easier and simpler to evaluate. You can generate many more samples compared to the true objective. But since the cheap and the true objective functions are correlated, you can use the model or information gathered from the cheap runs to help improve the tuning of the expensive ones. So the approach that GPTune band relies on is sort of combining the multitask learning LCM-based approach with this so-called multi-arm banded strategy. So this is a simple illustration where we're considering two tasks. So the front layer is one task, the back layer is another task. There's two tasks, and we can generate this so-called arms. There are 4 arms, and vertically that's the longer means the more samples in that direction. And the way it works, briefly speaking, is we can generate these different arms with different fidelities. For example, this S0 means this is the true object function. S1 means this is less expensive, less, I mean, it's a coarser one, and this is more coarser, and the coarsest one is S equal to 3. And we can use the LCM model to help generate some samples in this upper part. And once these samples are generated with their own fidelity, each of these arms will perform this so-called successive halving algorithm, which is essentially taking this collection of samples at the initial budget or fidelity level. For example, this is the budget level 3. We have this many of samples through this upper part. Then we'll do the successive halving by, so for example, taking 1/3 of the samples that are best performing, which may be these 3 red dots. And then we're going to push their fidelity to the next level, so making their evaluation more expensive. Then we do the evaluation. Then out of the 3, we also take 1/3 of them, the best performing one, maybe that's this one, and push it to the next level of fidelity. So this becomes the highest fidelity or the true objective function evaluation, and things like that. And in the end, each of the arm will generate a few best performing samples at the highest fidelity, and then we take the best out of the best as our final, winner. And as I mentioned, this can be done in multitask tuning sense, in the sense that here the LCM is built across different tasks and different fidelities. This is a little bit complicated, but I just want to give you a brief idea of how it goes. This is some example of the tuning the runtime of solving a convection diffusion equation on a regular n-cubed grid with AMG through Hyper. So the input space is this coefficients A and C, and there are 12 integer real or categorical valued tuning parameters, and we're looking at the runtime. And suppose we fix n, that's your true object function. And now we can decrease the n to make it a smaller grid, cheaper to evaluate the case as the low fidelity variant of the true object function. And here we're comparing again 10 tasks, so multitask, 10 tasks and multi-fidelity with the GPTune band. And here the dots showing the minimum found by a batch of the experiments. So it's comparing this multi-fidelity multi-fidelity multitask GPTune band versus multi-fidelity single task tuner called HP bandster, and we can see GPTune band wins out of 9 tasks out of the 10 tasks. And on the right, it's showing the comparison between this GPTune band with the single fidelity but multitask version of the tuner GPTune. And you can also see it's winning for 7 out of the 10 tasks. So meaning combining the multitask and the multi fidelity feature, we can win both of the tuners in both worlds. And this is a simple pseudocode that you can play with a little bit in the experiments. Here, this budget is defined as a constant. I mean, the range of the budget is defined as constant, Bmin and Bmax. And in the object function, we will take the budget and map this budget based on these bounds to the true mesh size of this n cubed, right? So writing a small linear mapping function and n cubed. Then with this budget, we map to this n. Then we call the application and generate the sample. And the number of samples per budget, or when to sample which function evaluation at which budget, is totally managed by GPTune. So that's all you need to launch this multi-fidelity variant. And the last feature I want to mention before the hands-on, second part hands-on, is the handling of non-smooth objectives with cluster GP algorithm, or CGP. So the idea is consider this a simple 1D function in red. So you can see it has this is a jump or discontinuity right here at x equal to 0. And as you may know, the GP is good only for smooth functions. And for this continuous function or piecewise smooth functions, it takes many samples to get a reasonably well approximation of the true objective. Yeah. And what you can do instead is you can find a way to identify these two segments or two partitions. And on each partition, it is a smooth function. So you can build 1 GP each, and then combine the two GP to get a combined GPU model for the whole function. And the way it works is every time you generate a new sample, you can specify something called exploration rate. So if that rate is higher, then you lean towards generating the next sample by random. If it's smaller, then you kind of want to use the acquisition function to get the next sample. The way it works is we will have the pair of observations x and y. Based on that, we'll use some sort of clustering algorithm to find these partitions. It's not meant to find this exact point very well, but even you can try it with different partitions that doesn't align with the boundary will help a lot. So once you get the partition, every new samples you need to classify which partition it belongs to. So it's a classification algorithm. Once that is done, we actually fit a component. We fit a piecewise GP on each of the partition, and when we do the maximization to get the next sample. So there's 2 ways of getting next sample. It's really important to kind of there's some trade-off, by tuning this exploration rate. And there's 2 key options. One is this one. The other is the number of partitions, or number of maximum number of partitions you need. So these 2. This is an example of again tuning SuperLU factorization time. This is a single task tuning scenario indeed, and and it's also a single objective, so it's only the factor time. We have 3 integer valued parameters. And this figure shows a comparison between single GP or this cluster GP or CGP. Essentially higher than 1 means CGP is better. And this for each of these matrices, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 matrices. The rightmost bar is the simple GP, And the rest are the CGP with different values of this uncomponent exploration rate. So you can see that these two are actually very critical, performance critical. But indeed, you can get much higher performance than single GP once they are chosen properly. So I think I'm this part two. Maybe I should walk through the hands-on for the part two. I think we're about 8 minutes ahead of the schedule. Is that right, Yang Hun?
I actually think you still have 30 minutes for the next session. So
sorry,
there's enough time.
Well, I mean, I think the presentation, second part presentation should finish at 4 o'clock, right?
Yes, yes. So there's still 10 minutes.
Yeah, I have about 8 minutes ahead of time.
Yeah.
So okay, let me go through these examples real quick. So you can start the hands-on if you want for the part two. So this is the part two hands-on. I should have been doing this, but yeah, ignore these comments. This is still running. So before I walk through the hands-on, any questions for the presentation? It's a collection of different, maybe very different topics. So yeah, whatever question you have, feel free to ask. Or maybe during the hands-on. Okay, so again, once you log into the Docker, we're here. So let's first go to this demo example, same example. And it's again in this bash script. So now we have done with the basic illustration. And let's use these ones to demonstrate the parallel performance. So you can see here, here is a different driver called Python driver called demo _ parallel performance.py. So what it does is it generates many tasks, 20 tasks, and minus 40 samples each. So it's a covariance of 800 by 800. And we're only going to run one iteration of the modeling and search to demonstrate how the performance can be different by either enabling the parallelism in the modeling and the search or not. So the first run will run everything sequential. The second one will run the modeling and the search in parallel. So we can just run that. Maybe I will increase my core count a little bit. Okay, let me try the Oasis account. Let's see. Maybe I think I can mark it's not here. I can do this. It's always a machine. Set it to 26 cores. So, so the first one is the sequential run. I think this will take about 2 or 3 minutes. So let's see whether there's any questions in the chat. Okay. And yeah, feel free to try it yourself in the meantime. So, let me just quickly go through what's going on in the part 2 of hands-on. So the first example, we'll use this synthetic function to demonstrate the parallel performance, and then we'll have this another synthetic function called OSY to demonstrate different ways of specifying multi-objective tuning or constrained multi-objective tuning. Then we have a super example to demonstrate the non-constrained two-objective tuning of two simple matrices. And then we have examples to show how the reverse communication interface script looks like. So we have a QR example, we have a super example. Then we use this synthetic demo function to demonstrate how to incorporate a coarse performance model. So here we're going to use some sort of a noisy variant of the true object function as some sort of a coarse performance model, just to demonstrate the workflow. And then we have again the synthetic function and the hyper real example to demonstrate how the multi-fidelity tuning approach works. And finally, we have this non-smooth tuning approach, CGP, using super reduced. Those are the 6 set of experiments you can try. So the hands-on, I think, start right now. It will last for 30 minutes. So once you went through all of them, you can also go into more details and play with the options of each of them. So. Let's see. It's taking longer than expected. It's selected because there's one compute node shared by all the participants. Okay, in the meantime, let me try the second one. So the second one is it's multi-object tuning. So we go to this folder. It's for a total of 210 samples. We're only going to run 10 iterations, those are 20 initial samples. I think this is because we're sharing the notes for that Oasis account. So perhaps if you wish, you can skip this experiment. All right, so this is the two object tuning with the synthetic function. So you can see in the end, it's outputting the optimal ones found. So each of them is a two objective, object one, object two. And you can change this to use a constraint version. So if you look at this driver script, you can see these are two objectives. These are unconstrained, right? So minus infinity to infinity. But if you look at the constrained version, you can see the object one now has a range, so it cannot be larger than minus 150. So if we this one by change the file name of this version. As there's new people joining, so if you maybe you can send the instruction one more time, all the materials. So right now we're at the part 2 of the tutorial. So maybe if you also send the the plan of the day, so that the newcomers know what's going on. So this is the constraint version, right? So you can see, actually, we don't have a way to plot it right now, but the achieved optimal will be quite different compared to the non-constrained one. All right, so this is two object tuning. So let's go back to the first one, which is parallel performance. I think this is now finished. So you can see there are two runs. This first one is sequential one, if you recall. And the search time is 240 seconds. And the model time is 64 seconds. And this one is the same experiment, but with parallel acceleration of the modeling and the search. And the search becomes only 5 seconds, and the model is only 7 seconds. However, the conversion is not that fair in the sense that the number of iterations is actually also run, case dependent, right? It's not exactly the same experiment, but still you can say, you can project the number to see that this indeed accelerates the modeling and such quite a bit. So, so that's the two object tuning for the synthetic function. Now, if we look at the super example, again, there is a run_examples.sh. Yeah, I think this one default one is two objective. Right. Yeah, so these are run out from the real application. So it's initially so this is simple setup. So only 5 initial runs. And there's 5 more iterations going on. The search is taking more than expected longer time. So let me just reduce the search time by reducing the number of generations in the search. So let's so just so Kim has a question. In the MO case, why are there 11 P? Okay, so so in the end of each tuning, it will show this OPT and OOPT are the optimal ones that are found. So in a single object tuning case, you only see one sample, but in multi-object tuning, it usually will generate a bunch of them. Again, these are the samples on the parietal front the tuner think it found. So so 11 means there are 11 points on that front that none of the samples dominate over any other in both objectives. Okay. So if we look at for example this case, there are 1, 2, 3. So 3 samples found that are optimal. So this one is this one takes the minimum time across the 3, but it's the largest memory, right? And this one is the smallest memory, but it's the largest time. And this one is in between. So that's why this is called the Pareto optimal configurations. Okay. So again, this is a multitask one. So this is the second task. And this is the first task. Again, for the first task, there are 1, 2, 3, 4 samples found that are optimal. Okay. So the next one, some example is this reverse communication interface. Let's say let's maybe just take a look at the SuperIO one. So it's using this one. Show you how the script looks like. So again, in the reverse communication interface, this is the driver script. So you can, in your case, you can copy this as a template and then fill in whatever your application requires. So this is the main loop, and every iteration will query this Python driver, which will read the database, do the modeling, do the search, ask for the next sample, and the real run is here. Suppose this MPI compiled code, then it will use this MPI run to launch the application, using command line options that are read from the database file. And then it will, this is the run log of each run. It will grab the time and the memory and read this time and the memory back to the database file. Matt is saying it's getting an error.
Yeah, I can post the error in the chat if it's not too long.
Sure, yeah, please.
It's saying it's this function GTMLA. Exception NS1 greater than NS.
So did you just run the script as it is, or you modify anything?
I did. Was I supposed to change something?
Sorry, you did or didn't?
I ran it as is, yeah.
Then that should, it's weird. Yang-Hun, can you help with Matt on this?
But maybe what I'll do. Oh, go ahead.
Yeah, let me try to figure it out.
All right, okay.
Thanks for the question, by the way.
Or I can try to run a fresh Docker and try it again.
Well,
I don't think that's necessary.
Yeah.
Okay.
Is this on the Oasis account?
Yeah.
Okay. All right. So let's run this RCI interface. You can see these are also logs from those SRAM MPL. Again, the good thing about the RCI is that you don't do code instrument of your application. Or if your application is not MPI based, but still some kind of distributed memory or cloud based, then I think this RCI interface is the best fit for you. And it also output, there are two tasks. There are best tuning parameters, best object functions. Because these are really simple, small matrices, these numbers are actually rounded. So this is just to demonstrate the functionality of the two object function, not meant to be any production run. Okay, so that's RCI. You can also try the Scalapack one. Again, this script. So you can see this is the 1000 by 1000 matrix, and we have 40 samples. Same as before. The main driver script is bash. Again, it's querying GPTune all the time, and it's calling the application without any code instrument by just doing an MPI run of the application.
Sorry, I see the issue now. It was my fault. You had said before to change the end runs to a smaller number, and I guess I made it too small.
Oh, that's right. Okay, I see. Yes. So
when I changed it back to the original number, everything runs correctly.
Okay.
That was my fault.
No problem. So I should have mentioned that because for that example, there's the unpaired, there's unrun. So unrun is the total number of samples. Unpaired is out of the unrun samples, how many are random. So you want to make sure that unpaired is smaller or equal than the untotal or unrun. I think that's what's the issue.
Thanks.
So you can see from the RCI interface, for example, for the Scalapack one, this doesn't have any run log for each run, but these are all output from the GPTune. So you can see every time it's query GPTune, it's loading the historic database and found how many are already there. And then based on the budget, which is 40 per task, it tells you how many it's going to be generated, generated. So in this case, it will generate 12 more. And next time it found there's already 29 in the database file, it's going to generate 11 more, and etc. This is about to finish. All right, so this one is done. So again, here it's 2 tasks. The first task, I mean, these tasks are random generated, but you can also specify them in the Python Bash driver. So the first task is a 265 by 70 10 sized matrix. Second one is this one, so a little bit larger one, and it found the optimal for both tasks with the multi-task tuning algorithm. One thing to mention is that not all the tuners are supported through the RCI interface, because it's really some sort of a reverse communication thing or checkpointing thing. So not all the tuners support the checkpointing. So currently it's the GPTune and the GP band. These two you can do the RCI model. What's next? Okay, the performance model. So here we're using the demo function. So now we use 42, 49. This compares running this synthetic function without or with the performance model. Let's see how. I think we'll have 10 more minutes for the hands-on before the second break. Okay, this is the first one without the performance model. This is the minimum fund. I'm sorry, this is the this is the minimum fund for the first task, and this is the true minimum for the first task by exhaustive search. So it's not too bad. So it's like a two-digit accuracy compared with true solution. But if we have the performance model, let's start those. All right. So this is the new optimal found. This is the true one, and you can see now it's almost 4 digits accuracy. Right? The coarse model is really helpful for this example. As I mentioned in the slides, for this particular example, the performance model is really just the true operating function plus some noise, just to demonstrate the usage. Because this is a synthetic function, it's really cheap to evaluate, so we just do this simple trick. Yeah. So you can see this is the true objective, and for the performance model, it's just adding a noise. So this is a very good approximation of the true objective. That's why you see with the performance model, the obtained minimum is much better. Okay. And then the next one is the multi-fidelity one. Here there's 2 examples. Maybe I will just try the hyper one. You can see that it's comparing 2 runs. The first one is GPTune, so it's a I think it's 1 task or 2 tasks. It's a single fidelity GPTune or the multi-fidelity GPTune band. So I should have mentioned that for the GPTune band, the number of total samples is kind of estimated by converting their cost to the highest fidelity for each of the sample, and make sure when we do the comparison, make sure the number of samples, the equivalent number of samples at the highest fidelity are the same across the 2 runs. Yeah, these are output from each of the hyper run. So this is the one without the multi-fidelity tuning. That's this number. So while I'm demonstrating this and while you are experimenting, Yang Hui is going to send a Google survey for this tutorial. I mean, we'll have another session as a part going on that will come on soon. But if you have time during the break, you can feel free to fill it out. It basically will ask you, what applications are you interested in, and how do you feel about the tutorial, and how can we improve, making improvement. And here you can see it's a simple 100 cubed small example, but some evaluation can take much longer than expected. Yeah, so Yang just sent out the survey. It's going to ask you what the applications you're interested, and the type of the tuning parameters you're interested, the characteristic of the object function you think, and the features you're interested in GPTune, essentially the ones in part 2 and part 3 that we talk about. And some suggestions of the tutorial.
I'd like to mention that these are optionals, and you can skip some questions if you do not like to answer the questions. Thanks.
Hey, this is Matt. Just a quick question. I noticed in environment you can specify CPU, GPU. Are there certain multi-objective learning problems where utilizing the GPU speeds it up dramatically, or how
that's a very good question. Yes, I mean for this Docker image, when we built it, we didn't prepare any GPU examples that are runnable. But if you're interested, you can look at this super dist RCI example folder, and there are examples of actually two object tuning examples with for SuperU with the GPU enabled. But I don't think you can run it right now because it's not compiled with GPU.
That's okay. Yeah, so there are examples there. If I can set it up on a GPU Linux server, then I can try them out.
Yes, exactly. Yes.
Okay, gotcha.
Yeah, so there's the one, if you look at the, so there's the one, these two are two objective tuning with GPU, and this one is a single objective tuning with GPU. Yeah, so
okay.
Yeah, you can look at our, maybe our user guide or online instruction to see how to install GPTune manually. And once that's done, you should be able to run this.
Oh, I see. Because your Docker file is set up for a CPU only environment. I need to construct a Docker file that would allow for GPU.
That's right. I mean,
okay.
In fact, you can just use this Docker and rebuild everything by, I think by using this configure file, config clean linux.sh. Here you probably want to, here you can see that we're actually compiling the GPU enabled applications individually, so you can enable the GPU for each of them. And rerun the script. Yeah. So just let us know, maybe via email after this tutorial, once you have trouble using this.
Okay, thank you.
Okay, now we're at the 10-minute break. This one is still running, so all right. Just so you know that the third part will be talking about the historical database and some of the crowd tuning features. For example, transfer learning using the existing database on another machine, or sensitivity analysis by looking at the historical database and tell you which parameter is most important for your application. So the third part would be, let's see. So third part would be 50 minutes with 20 minutes presentation and a 30-minute hands-on. Then depends on how it goes, so we can perhaps save the final 30 minutes if not needed. Okay, this is done. So let's see. Right, so this is the one from single fidelity, which is the minimum is 1.1 seconds. Then multi-fidelity for the same task, it's all right, it's 4.8. I think these are set up just to demonstrate the functionality. It's not meant to show the performance because it's a very simple two examples. Anyway, okay. So the last one is the cluster GP one. We'll use the separate example again. This will just run CGP. This will just demonstrate how how CGP looks like. So it's 20 samples. I think for 201 simple example. Here, still doing the clustering of the partitions, doing the acquisition maximization, and doing the sample. So it's actually 2 tasks, but CGP doesn't support multitask yet. So it's essentially doing each task individually. So you can see it's the same similar type of output after it's finished. Okay. So I think I'm going to stop sharing, and Yang-Hui, you can take charge from now. I think we have 2 more minutes to start the next. Is that right? 2 more minutes to start the next part.
Yes, that's right. Okay. Thank you very much, Yang, for the nice tutorials.
Yeah. So if you still have any questions, just send me chat, and yeah, I'll try to answer.
Yang, can you see the screen?
Yes, I can see the screen.
Okay. Okay, let me start the part 3. So thank you everyone for joining us today. The part 3, we will discuss our database support for autotuning and some interesting features using the history database for enhancing some autotuning capabilities. My name is Young Cho. I'm a postdoc at UC Berkeley. So let's start. So we have studied GPTune autotuning framework, which is a Bayesian optimization-based autotuner with some advanced features like multi-task learning and multi-fidelity tuning and multi-objective tuning and so on. So our goal is to find the optimal tuning parameters within a limited number of evaluations of the code, because the HPC codes are very expensive to evaluate. So the idea is to use a surrogate performance model, which means that we can build a performance model using performance data samples obtained for multiple number of function parameter configurations. So once we have a surrogate performance model, we can choose a promising parameter configuration, and then we can run and evaluate the application for the parameter configuration, and then we can record the function evaluation research in some DB. And then once we have more performance data samples available, then we can further improve the surrogate performance model. So this was nice, and we have applied GPTune for many interesting ECP problems, tuning problems, but autotuning is still a very expensive task. And so the thing is that the tuning quality depends on the number of function evaluations, but HPC or ECP applications are still very expensive to evaluate. And in addition to this, autotuning also needs to be done for every different system. Like, users who are using different platforms need to run autotuning individually or separately. So this is very expensive. So therefore, we are building GPTune history database, which is to harness the power of the crowd in autotuning. So basically, GPTune history database is to share performance data samples among different users on different HPC systems. So as shown in this figure, there are many users who might use different machines and there will be performance data samples obtained from different machines. And GPTune history database is a shared repository and interface to enable data sharing between multiple users. And so our history database enables several interesting and useful scenarios. So for example, our database can be used as a shared performance database. So this means that users can query the best-tuning parameter configuration or a pre-trained surrogate model obtained from the crowd. And also users can use our database as a cloud DB for checkpointing or restarting of an auto-tuning process. And we also use this history database to enhance the GPTune package. And we have several interesting features. So for example, transfer learning means that we can learn knowledge across different users and different platforms for auto-tuning. And sensitivity analysis means that we can estimate the importance of the tuning parameters using historical data collected from the crowd, collected from the many users. And in this slide, I'm going to explain how GPTune can be run with the history database. So this picture shows the basic workflow of the GPTune Bayesian optimization process. And we start with saving or loading performance data samples in using the user's local storage. So in particular, we record the obtained function evaluation research and trained surrogate performance models in the user's local storage. And we also record some more information for reproducibility. So this means that for reproducibility of the performance data, we can record the machine configuration, like the number of compute nodes and the number of cores used to run the application. And also we record the software configuration, which means what kind of software packages are needed to run the application and what are their software versions. So using this information, people can reproduce performance data. Also, users can use this information in order to determine which data set is more relevant for transfer learning. And finally, GPTune has also some interface so that GPTune process can upload and download some performance data using the shared repository running on the cloud. So yeah, that's the how GPTune works with the history database. And in this slide, I'm going to show a high-level view of the database format. And as I mentioned, we maintain two types. We mainly maintain two types of information. So function evaluation research and the trained surrogate models. So for example, for each function evaluation research, we record the task parameter, which defines the size of the input problem or the input data. And also, of course, we record the tuning parameter configuration and each evaluation research. And as I mentioned, we record the machine configuration and the software configuration for reproducibility. And in this example, as shown in this figure, this means that, okay, this function evaluation is done using Nurse Corey machine, and we used hardware CPU nodes, actually one CPU node, one compute node that contains 32 physical cores. And this label means that, okay, this is using scale-up pack version of 2.1.0. And for surrogate models, we mainly record the hyperparameters of the model so that users can reproduce the same model using the hyperparameter information without needing to train this model again. And there are some additional model stats information like log likelihood or gradients information, which means that we can use this information in order to determine which surrogate model will be more accurate or not. So this is the high-level view of the our database. And so when you are building this system, one of the significant challenge was to achieve the reproducibility. So in order to help this, we support some automatic parsing and recording of the environment information. For example, for software configuration, if the application is running or installed or running using CK or spec, then we can automatically detect the software dependency and record the software version information in the database. Also for the machine information, if the application is run by the Slurm workload manager, then we can also record the allocated node information and the basic architectural specification in our database. But if this is not the case, then users need to provide this information manually. But there are still some other challenges. For example, there might be some ambiguity of the software and machine names in the database records. So for example, for the nurse coarse hardware nodes, some people might want to use the name like hardware, but some people may use like Xeon E5, which is a the Intel processor family name. So there's some ambiguity here. So in order to solve this problem, we also have some separate databases for existing software and machines, for popular software packages and machines. Then we also have some internal tag name matching system in our cloud repository so that we can remove some ambiguity there. So I'm now going to talk about some our interfaces. We mainly have two kinds of interfaces. The first one is the web dashboard, which is a very user-friendly interface. So our database is already in service at gptune.lbl.gov. And if you click on the history database button here, then you can use our web dashboard. That's basically an interactive data table that you can play with the queried performance data samples. And there are some other useful features here, like make prediction or sensitivity analysis, which means that you can run some performance prediction or sensitivity analysis using a web browser. So I'm also going to show this feature after the presentation. And another useful interface is a programmable interface, which we call crowd tuning API. So which means that you can access our database and use some data there in your programming language like Python. And that's the crowd tuning API is mostly a collection of Python wrapper functions that run with an API key. So the API key means that the user information. So every user has to have an API key in order to use the crowd tuning API. And users can obtain one or more API keys using our website. And this code snippet shows an example that queries function evaluations from the history database and returns a list of dictionaries, so called query function evaluations. So as you can see from this figure, so there is a API key. So you provide your API key here, and you also specify the tuning problem name that you want to search or that you want to query. And the problem space is a dictionary to describe the ranges of the tuning parameter configurations that you want to search. And the configuration space is to describe the machine and the software configurations that you want to allow to download or access. So, the crowd tuning API also includes some other useful functions. For example, query surrogate model can query a surrogate performance model as a black box function in Python. And the query predict output can make a performance prediction for an arbitrary parameter configuration using the data in our cloud database. And query sensitivity analysis, that runs a sensitivity analysis, and as I mentioned, but I give some more details in some later slide. And we also try to maintain reliability and security of our database. And so we support a different level of accessibility of the performance data, which means that performance data can be publicly available or private, and also shared with registered users or specific user groups. And for reliability, for now, only certified users can upload any data, and the owner information can be displayed. But we also provide some option for users who do not wish to disclose their information in the our cloud repository. And we've implemented our database securely, and our database uses the NERSC resources to operate our framework, and we also often get some feedback from the NERSC experts for building this framework. And I'm now going to talk about some interesting use scenarios of the history database. One of the most interesting scenario is transfer learning based autotuning, TLA, with GPTune history database. So this can actually improve the tuning quality of GPTune using the data in the history database. So as you can see from this figure, our database contains or will contain research obtained from many different users who are using different machines or different problem sizes. And using our crowd tuning API GPTune can transfer data across different tasks. And GPTune supports several TLA methods, such as LCM-based multitask learning or linear regression-based transfer learning, and so on. But I'm not going to talk about these different methods. But I'd like to say that the LCM-based multitask learning can actually model the relations between different tasks quite well. And we have some interesting experimental research as well. So, yeah. So we have some numerical research to show the benefit of the transfer learning approach. And this is one example of ScaleupX PDG QRF routine tuning. So in this scenario, we consider the same machine settings, but we assume, so in our database, we have collected performance data samples for different problem sizes. And in this figure, we compare the tuning research, the performance of the best tuning research after the 20 function evaluations, and we compare our transfer learning schemes with a single task learning, which is SLA here. And so single task learning does not use any historical data in our history database, but TLA can reuse historical data obtained for different task sizes. And TLA worst here means that we choose the worst historical data set, but TLA best means that we choose the best historical data set for transfer learning. Excuse me. So the x-axis here represents the different scenario, and the y-axis here represents the performance of the after the tuning. And here, if you look at the geometric mean of the these options, you see that transfer learning best can actually achieve like 40% about 40% improvement compared to the single task learning. And we have also numerical research for transfer learning across different machine settings. So here we tune the Nimrod, which is a fusion simulation code and requires a lot of computational resources to solve the problem. And here we consider that we have collected performance data using 32 Haswell node on the NERSC core machine, and we are now going to tune this application on 64 Haswell node and 64 KNL node, which means Intel Xeon Phi architecture. So, and we also compare the tuning performance with a single task learning that does not use any historical data from our history database. And the plot is a little bit different here. So x-axis represents the number of function evaluations, and the y-axis represents the best tuning research, depending on the number of evaluations. And since the tuning research represents the runtime of the application, so the lower is the better. And so there are two different transfer learning approaches here. That's because our GPTune framework supports several different methodologies. But you can definitely see that the transfer learning approaches can significantly improve the tuning quality compared to the single task learning. And so, okay, so I'm now going to talk about the sensitivity analysis. So in here, we particularly use the Sober's sensitivity analysis, which is a variance-based analysis that estimates the importance of each variable, each tuning parameter, and also interactions of the variables or the tuning parameters. And the Sober's sensitivity analysis will return some indices. So for example, the S1 is the influence of a single tuning parameter. So the importance of a single parameter, and ST means the importance of a single parameter, but it also includes all interactions with other parameters. And in practice, for some HPC applications and ECP applications, we found that the ST index can actually provide a nice insight on the tuning parameters. So for example, if you look into this table here, super LUDist, there are 5 tuning parameters, and looking at the ST indices, we see that the column permutation and MP row parameter and the number of super node parameter are important compared to these other 2 parameters like look ahead and number of relaxation parameter. So based on this, we can refine the tuning problem or reduce the tuning problem space in order to achieve optimal tuning parameter configuration within a smaller number of evaluations. And also for sensitivity analysis, you can use either our web interface or the crowd tuning API. So here is one numerical experiment that shows the benefit of reducing the tuning problem space using sensitivity analysis. So here, the blue line indicates the original tuning problem. So that contains original 5 tuning parameters. And the orange line represents the reduced tuning problem. So as I mentioned, the Sober sensitivity analysis says that, okay, the 3 parameters are more important. So in this orange line, we only tune the 3 parameters. Other 2 parameters are using the default values. So again, the x-axis represents number of evaluations, and the y-axis represents the best tuning research, which is a runtime of the solver. And we see that the orange line can actually attain good tuning research using small number of function evaluations. So that's the benefit of sensitivity analysis. So I'm a little bit over 20 minutes. So our next step is to make this framework more sustainable. And we are working hard to deploy our framework to more real-world tuning problems. And for now, we currently focus on tuning problems in the XSDK package, which contains lots of interesting tuning problems. But we are also interested in seeing more useful scenarios as well. So this is an acknowledgement slide. So this is part of the ECP project. So I think we can now start on the hands-on sessions. But if you have any questions about the presentation, I'm happy to answer the questions. And thank you very much.
I have a quick question. It may not have a quick answer. Can you use GPTune with abstraction layers such as Cocos or Raja?
Sorry, I'm not actually familiar with Cocos and larger.
Raja, yes. Yeah.
I
can try to address this. This is Sherry. Can you be a little bit more concrete? So for example, your program is written in Cocos, right?
Or yeah, let's say an application that uses Cocos as a third-party library.
Sure. And then there's no problem with that. So essentially, you will need to write a little application code hook with the Python code. So your code needs to be Python interface hook with the GPTune, the Python driver. And then we will run your application code on any GPU with the Cocos backend.
Okay, could you repeat that? I didn't quite grasp. Could you, just say that again? I didn't quite understand.
So Yang, do you have a picture of how the GPTune will call the application code?
Yes. So let me precise. Is your code MPI based or it's a shared memory?
No, it's Cocos. Cocos can run on MPI and also any GPU. So it's a portable layer to GPU.
Okay. Sure. Yeah. I mean, Yang Hun, can you?
So you would, in effect, I guess, in this scenario, one would in effect be tuning the abstraction layer itself.
That's right.
Yes. As long as you have a way to, pass the tuning parameter from Python to your code, either through, command line or even variables or, input files, and then it should work.
So you see this picture, there's a defined objective function, right? Do you see that?
Let's see, it's in the blue.
The blue, there's to say define application as a black box function.
Yes, I do see that.
Yeah, so here, so your Cocos application, you need to install yourself. And then we will find you will expose the parameters to GPTune. So we'll essentially treat your Cocos application as a function taking some input parameters.
Okay.
And then we'll keep running every time. We'll change the parameter from GPTune side, and then we'll call your Cocos application code.
Okay. So I would have, in other words, I would have to expose the Cocos features to GPTune that I would want tuned.
You want to tune, yeah. So Cocos, for example, I don't know, for GPU side thread block, those GPU kind of parameters, you can just expose that interface to GPTune.
Okay. All right. I might follow up with you guys after the meeting on how I might put an example together like that.
Yeah, we can start with a very simple example.
Yeah, that's just to illustrate concept. Yeah.
Yeah, so in your simple example, you can probably just say which one parameter you want to tune from the Cocos side. Yeah.
Okay. All right, that makes sense. I would have to, it would take me some time to put together a simple example, but I can probably do it pretty quickly. Yeah,
you can, before you do this interface to Python, you can just have the simple example to be able to run, then we can take a look. And then we can, work email to see how to do this hook. Okay. Could you drop your email in the chat and I'll follow up with you on that? Sure. Yang, maybe you can drop mainly Yang. We can drop several. Yeah.
Thank you.
So if Amy is willing, would it be reasonable to share this eventually in some collection on our webpage so that other people can see how to do it?
Oh, sure. You know, but I think it will take me a while to figure out how to do it. My first thought would be to maybe try it with a mini app, like one of the ECP mini apps, or maybe something even simpler than that.
Sounds good.
I'm sorry, who is that speaking?
Jim Demmel.
Okay, cool. I'm not. All right, I see you there. Okay, thank you. Let's see, I see. Let me put my email in the chat. Oh yeah, there you are, Sherry. I see it. Very good.
Thank you.
Thank you. That's very cool.
Okay, thank you for the questions. Are there any more questions? Otherwise, maybe you can start some demos of the history database framework. Okay. So before starting the demo, I'm gonna introduce our website here. So you can access gptune.lbl.gov, and there's some information. So in our entrance, our index page, there are some tuning examples of the history database. And so we have been using the history database for Scalapack and SuperDisk, Hyper, and Plasma, Slate, and Nimrod. And there are some more applications in other domains like randomized linear algebra. There's some about page, and there are GPTune user guide and another user guide for the history database framework. And so you can basically access this history database session for using the history database, but actually you need to sign up in order to use all the features of our framework. So for this tutorial, we've made a number of tester accounts in, let me see. So in the hands-on part 3. So, okay. So we have assigned one tester account for each participant. So you can use your account here. So for example, you are also welcome to sign up if you like. So after signing in, you can use the history database feature. So you may want to visit the performance data browser here. And our first hands-on session is to use the web dashboard for the Nimrod application. So let me see. So if you go to, if you click on the performance data browser, then you have this selection options, and please choose the Nimrod application. Then it will show a number of different configurations. But here, for now, in our database, we have only one machine configuration and also one software configuration. So as shown in this dictionary. So if you click on the search button, then our dashboard will show you some performance data samples. And this is an interactive dashboard. So you can actually see some more details by putting your mouse cursor here or there. And you can also do some sorting for the obtained performance data. So for example, so since this application is minimizing the runtime, so you can just sort the runtime and then you can find the best tuning parameter configuration from the database. And there's some also owner information. And as I mentioned, you can place with some performance prediction or sensitivity analysis using performance data available in our framework. So for example, you can click on the sensitivity analysis button, and there's some more information about the about this analysis method. And you can basically choose one of the input problem, and then you can set some range for surrogate modeling, and then you can run this button to perform this analysis. So maybe I can wait for like a couple of minutes and then I can answer questions if you have some specific questions. Also, you can make some performance predictions using this database. But as I mentioned here, you need to make sure to provide all the values for each data field. So let me put this actually here. And so basically, you can set any number here, depending on the range for modeling here. So if you click on this predict output button, then you can see the prediction result from our database. So this may take some while. Yeah. So this means that for this parameter configuration, the predicted runtime is 270 seconds. So how many minutes I have? And also the next scenario is crowd tuning API. It's to demonstrate the features of the crowd tuning API. And one of our scenario is that, okay, so when you run GPTune Autotuner, you can automatically upload function evaluation research in our database, in our history database. So if you are using our Docker image, then you can go to this directory, examples, crowd tuning, and demo directory. And here are the steps. So first step is to export the crowd tuning API key. So as I mentioned, you can use an API key here. So you can create an API key for you. So this is the API key. So you can export this API key in the Docker container. And then you can just run this one, run tutorial linux.sh. And this will do a tuning on the demo function, and then it will also upload some performance data in the repository. So you see the log there. So direct upload success. So let me see. So if you go to our browser again, and you can find some performance data for demo tutorial. So yeah, I'm now seeing that there is one user already submitted some data here. So this is the data I just submitted. And so this is very nice. So let me search this. So this scenario is actually uploading 20 function evaluations. So I think 20 is mine and the other 20 is from the tester 2. And so we can also sort data depending on the user. And also you can play with some sensitivity analysis or performance prediction using this data. And another scenario is crowd tuning Nimrod. Again, so I've already explored the crowd tuning API key here, so I can just execute this one. So this is just a functional check for the crowd tuning API keys, API functions like query function evaluation research, and run a sensitivity analysis, and query a surrogate performance model, and make a performance prediction in your programming language. So rather than using a web browser. Oh. Oh. So sorry, maybe you need to also need this comment. So if you have not done this yet, please also execute this comment before running this Python script. I'm sorry about this. So, for example, this Python script will return a sensitivity analysis feature in some printed format. So, the last scenario is a transfer learning feature using performance data samples in our history database and do an auto tuning with that. So, crowd tuning, if you go to the crowd tuning demo directory, and then you can run this script, run experiment Linux. So basically, this script, this scenario will download performance data samples in this directory, in this tuning problem, GPTune demo, where we have hundreds of function evaluations for this function. So, and this will compare tuning research between single task learning and transfer learning. So this one, 0.97, which is a result from single task learning. Now it's running transfer learning using a linear regression-based technique. So this is unexpected, but there is some error message. But let me rerun the script after this, and it's now running our LCM-based transfer learning. Yeah, so the research from transfer learning is 0.74. So since the single task learning's output was like 0.9 something, so it clearly shows the benefit of transfer learning using some historical data. It's really weird why the regression mode was showing some error messages, but I think if we run this again, then maybe there will be no error. So I think this is basically the end of the hands-on session. So I think we can also start discussing something if you have any more discussion points from the people.
Yeah, I just want to remind everyone that if you have time, please fill out our online survey. It's really important for us to improve our codes. Thank you.
Yeah, so also now the regression-based approach has also succeeded executing the experiments. So the research is like 0.76, so which is quite similar to the LCM-based approach, but this one is slightly worse than the LCM-based transfer learning. So, yeah. So I think I can stop sharing now. So there are still three attendees here. So thank you very much for staying like 3 hours in this room.
I think maybe we can, just stay for four more minutes. If you have questions, we can just set up a one-to-one meeting or email chat with us. Yeah, I guess we don't have to stay for another 30 minutes.
Yes.